Hello everyone, I am Anushka from KL University. As a part of my embedded systems internship at Emertxe Technologies, I worked on a project titled EV ADAS system, real-time EV dashboard and ADAS warning system using STM32 Bluepill, PixSimLab and Python dashboard. In this presentation, I will briefly explain the project architecture, implementation and the results achieved. This project focuses on improving electric vehicle safety through real-time monitoring and driver assistance. Advanced driver assistance systems improve vehicle safety by monitoring the surroundings and warning the driver of potential hazards. In this project, we monitor EV parameters such as speed, battery SOC, torque, and temperature while detecting obstacles using ultrasonic sensors. A Python dashboard displays all information in real time and provides collision and blind spot warnings. System architecture. The system starts with PixMLab, which simulates the EV environment. The STM32 Blue Pill reads sensor data and processes it using the EV controller, ADAS engine, and fault manager. Finally, the processed data is sent through UART to a Python dashboard where all vehicle parameters and warnings are displayed in real time. Hardware and software. The main hardware includes the STM32 Blue Pill, ultrasonic sensors, potentiometers, LEDs, and buzzers. Software tools used are STM32 Cube IDE for firmware development, PixSimLab for simulation, and Python with Matplotlib and PySerial for a real-time dashboard and UART communication. Project timeline. The project was completed in 14 stages. We started with tool setup and sensor interfacing, followed by timer configuration and EV controller development. Next, we implemented the ADAS engine, fault manager, UART communication, and Python dashboard. Finally, all modules were integrated, tested, and demonstrated successfully. The main algorithm used is the time to collision (TTC) calculation, where TTC equals distance divided by speed. Ultrasonic sensors calculate obstacle distance using echo time. Vehicle speed is converted from kmph to meters per second, and battery range is estimated using the SOC. These equations help generate collision and blind spot warnings. Dashboard and ADAS features. The Python dashboard displays vehicle speed, battery level, motor temperature, torque, and estimated range. It also provides a bird's eye view of nearby obstacles, shows blind spot indicators, calculates TTC, and generates virtual alerts whenever an object is detected. Testing and validation. The system was tested by validating sensor readings, obstacle detection, UART communication, and dashboard updates. Collision detection, blind spot detection, and warning alerts were verified under different conditions. Implementation and results. The complete system was successfully implemented by integrating the STM32 firmware, PixMLab simulation, and Python dashboard. The system accurately monitored EV parameters, calculated TTC, generated collision warnings, detected nearby obstacles, and displayed all information in real time with stable UART communication. Let us look into the Now let's take a look at the STM32 implementation of EV ADAS system. After opening the STM32 Cube IDE, we need to configure the microcontroller. This is the IOC file. IOC is input output configuration file. This is used to configure the GPIO pins, ADC channels, timers, UART. After configuration, we need to save the project. And then we are dividing this big project into small modules. So after configuring the peripherals using .ioc file, it automatically generates a project file such as main.c, which is present in the code. This is the main.c file. Since the project is large, we don't write all the code inside main.c. Instead, we divide the project into separate source and header files, making the firmware modular easy. So in the INC and SRC, we have smaller modules such as fall.c, ADAS.c, evcontrol.c, uartshell.c, and the same with header files here. evcontrol.c calculates vehicle speed, torque, battery, SOC, motor, and ultrasonic.c interfaces with three ultrasonic sensors and measures front, left, and right obstacle distances. And ADAS.c implements ADAS features such as TTC, time to collision, collision warning, blind spot detection, and parking assist. Fault.c detects faults like monitor overheating, low battery, sensor failure, and collision, and control LEDs and the buzzer. uartshell.c handles UART communication, transmits EV telemetry to the Python dashboard, and processes UART commands. Finally, these modules are called from the main.c, where all the functions are integrated to execute the complete EV ADAS system. Now we need to build the project by right-clicking on the project EV dash, build project. CubeIDE compiles all source files. If there are no errors, it generates the binary file. As there are no errors, the binary file is now generated. Now, this is the PixSim lab. After launching the PixSim lab, we need to select the STM32 Bluepill board and load the binary file. Now, this is the PixSim lab spare parts where all our inputs and outputs are present. We have the potentiometer with accelerator, brake, SOC, and temperature. And we have three ultrasonic sensors, front, left, and right. Its purpose is to measure obstacle distance and calculate the TTC. And accelerator controls vehicle acceleration, brake reduces speed, SOC simulates battery as state of charge, and LEDs. Red indicates critical collision warning, yellow indicates system fault or motor over temperature, blue LED indicates left blind spot, and green indicates right blind spot. And the buzzer, its purpose is to give an audible warning during collision or a fault. And now we can observe the output in the virtual terminal. If you see here, as we are reducing the front distance to less than 30, the red light displays. As we are reducing the left distance, blue is indicating. And when we are reducing the right and increasing the left, green displays an alarm. If you can see in the virtual, alarm 3 is activated. And when front distance is less than 30 or TTC is less than 3 seconds, the red is displayed, a warning alarm. Now let's open Python dashboard by running python ev dashboard.py in the command prompt. As we change the parameters in the spare parts of Pixim Lab, we receive live data in this Python dashboard, EV ADAS dashboard. As you can see in the left side, it indicates speed, and in the middle, it indicates EV metrics, torque, acceleration, brake, motor temperature, alarm, fault. And in the right side, we have bird's eye view where we can see if there are any obstacles, and if the obstacles are nearby, and if it is ready or nearby to collision. It measures using the ultrasonic sensor and gives us an alarm. As you can see, TTC is 0.2 seconds. The dashboard calculates and continuously displays the TTC values. TTC is distance by time. As speed increases or obstacle distance decreases, TTC decreases. And we have three alarm indicators: green, which indicates it is normal; warning is in the color of amber; and critical is in the color of red. As you can see, as the left distance is reduced to less than 30 centimeters, left blind spot indicator is turned on, which is in the color of amber. If we reduce the right blind spot distance, as the left blind spot distance decreased, the blue indicator is on. Now let us increase the left distance and decrease the right to less than 30. So we have a green indicator on, which indicates right blind spot. These indicators warn the driver about vehicles or obstacles nearby. And now you can see the alarm is indicated to none because all the distances are more than 30 centimeters. And you can see a live graph in the left side which displays vehicle speed over time. Now, as you can see that as the front distance is reduced to less than 30 centimeters, we can see that the alarm is giving an indication that advisory. As you can see, there is a collision in the front side of the EV vehicle in the bird's eye view. Now we have successfully implemented the EV ADAS and the simulation of the EV ADAS is also completed. Thank you so much.